All right, so we finished section 5 today. Well, once you watched this video. In class, we proved the alternate series remainder theorem. And then we learned that this alternating harmonic series, which we all convinced ourselves converged to the natural log of 2, can be rewritten, and we convinced ourselves that this set of terms will exactly have a one-to-one correspondence with this set of terms. So it's the same, and yet when we grouped them and rewrote with some arithmetic, we showed that that series, which converged to the natural log of 2, is actually equal to 1/2 of the series which converges to the natural log of 2. So these terms were the exact same series as these terms. So we're saying that the natural log of 2 is equal to 1/2 the natural log of 2, which we know is impossible. So what are we dealing with here? Well, what we're dealing with is a series which converges, but only conditionally upon how we associate those terms. Now keep in mind that for any finite number of terms, how we associate them doesn't matter. A sum of terms, some positive and some negative, no matter what the order, will always be the exact same answer. But when it's an infinite series that converges conditionally, then we have what we just saw with the natural log of 2 and the alternating harmonic series. This is called conditional convergence versus absolute convergence. So here's the definition. Some series converges absolutely if when all of its terms are positive, that series also converges. If the absolute value of a series terms here converges, then we know that the terms themselves will converge, and they'll converge absolutely, whatever that means. We'll learn in just a minute. On the other hand, if a series converges conditionally, well, that will happen when the series of the absolute value of all of its terms actually diverges. So in other words, some series may have some negative terms in it, and that series may converge. But if you make all the negative terms positive, if that series diverges, then your converging series converges conditionally. So we have our alternating harmonic series as an example. We know that this series converges to the natural log of 2. But if you took the absolute value of these terms, then it's the diverging harmonic series. So since the absolute value of the series doesn't converge, our converging series converges conditionally. On the other hand, if we consider this infinite geometric series, the R value is -2/5, and the absolute value of the R value is less than 1, so this series converges. Now, could we rearrange the terms of this sequence, -2/5 plus 4/25 minus 8 125 plus 16 625, etc.? Could we rearrange those terms and get something different? The answer is no, because even the absolute value of those terms converges. So when the absolute value of the terms converge, your original series converges absolutely. So what are the practical implications of this? The practical implications are these properties. When a series converges conditionally, then you can rearrange the terms to get that series to converge to any real number. However, if a series converges absolutely, then the terms in any ordering will only converge to the same one value every single time. All right, let's ask the question, does the series diverge, converge conditionally, or converge absolutely? For our first example, I hope you'll recognize this as a geometric series. This series is geometric. The first term is -1/2. The common ratio is times -1/2 times -1/2 times -1/2. In other words, we could have rewritten this as the sum of the value negative 1/2 to the nth power. It's the same thing, and you can see more clearly now that it's geometric, and the absolute value of r is 1/2, which is less than 1, so it converges. So this series converges. So the question then becomes, does it converge conditionally or absolutely? And all you need to do to answer that question is ask yourself, well, what about the absolute value? You don't have to show this. You can just, in your head, say that the absolute value of the terms is essentially just 1/2 to the n. Well, it's still a converging geometric series. So not only does our alternating series converge because it's geometric and the absolute value of r is less than 1, but also the absolute value of those terms is a series which converges because it's geometric again. Therefore, this series converges absolutely. All right, let's take a look at another example. How about this alternating series? It alternates. Right away, though, I hope that we notice that as n approaches infinity, a sub n, which is just the 3n plus 5 over n plus n minus 1 part, converges to 3, which isn't 0. So our answer here is that this series diverges, and it diverges by the nth term test for divergence. Let's look at another. All right, so what do you think about this series? Well, it's definitely alternating. The terms are getting smaller with each successive term, and the terms tend towards 0. So this definitely converges by the alternating series convergence test. However, does it converge conditionally or absolutely? So to answer that, all we need to do is check out the series where we take the absolute value of all those terms. So that's the series of the absolute value of these terms. And this is a p-series where n is a half. So that diverges. And therefore, our series converges conditionally by the alternate series convergence test. And that's all we are asking in these types of problems. We don't ask you what these p-series converge to. We just want to know if they converge, is it conditionally or absolutely? And when the absolute value of the terms diverges, your converging series converges conditionally. And when the absolute value of your terms also converges, then your series converges absolutely.